Okay, welcome back. Today is April 29th. Happy Friday. Today we're going to cover Taylor's series. Last class was Taylor polynomials. Those had definite ending points. Taylor's series are going to go forever, infinitely many terms. Okay, that's the only difference. Next class, we're going to do some applications of Taylor series. And Monday's class is the last day for the new material before the test. Wednesday coming up is our review day for Friday's test, 1 week from today. Definitely not too early to start studying for that one. I will share something very personal with you. When I was a Calc 2 student myself in college, my teacher dropped the lowest test grade. I think there were 4 tests during the semester, and I got A's on the first 3 tests, so I knew that it didn't make any difference what I got on that last test, which was on all the series stuff that we've been doing. And so I didn't study for it. My grade was 14 on that test, lowest grade I've ever gotten on a math test. Now he dropped it, so it didn't affect me. But I didn't really learn series until like years after that because I was never inclined to go study it. So I'm not dropping any tests in this class, and you're welcome, so that you can learn it now instead of falling into the trap that I fell in and getting a 14 on the calc test. All right. Also coming up next class, project number 8 is due. Okay, so that's the one that you're working on series. Okay, so let us start at the top of page 54. Oh, I just finished grading the last quizzes, so I'll give them out today. Okay, in this class, we investigate Taylor series. We'll look at what happens to Taylor polynomials as the degree approaches infinity. Number 1, last section, we did these Taylor polynomials that had definite stopping points, for example, degree 4. In this section, we've got series, and we're going to let the power go to infinity. So in this complicated looking formula, it's just the thing that essentially you proved last class. It's got a definite stopping point at n, but we're going to let this thing go to infinity. Okay, more and more terms. What's that? Always of that form, and we'll just let the number of terms go to infinity. For example, in number 2, let's find the Taylor series, including the general term for f of x equals e to the x near a equals 0. So we're going to start that right there. So before we plug into our crazy formula from number 1, let's just start doing our calculations here. We need f of x, we need f prime of x, f double prime of x. How about we do 4 derivatives here, and then we'll see if we can establish our pattern. By the way, the primes get unwieldy pretty quickly, and so standard thing is to indicate a higher order derivative with the number in the parentheses. Well, it is a pretty easy pattern in this one, yes. All right. So the original function, I'm just copying, it's highlighted, it's e to the x. What's the derivative? E to the x, second derivative, e to the x, e to the x, e to the x. Okay, a common pitfall I've seen for past students is to take that e to the x, for example, this guy right here, let's say. That's the second derivative. We know the second derivative goes right up there, and so they'll write something like this, e to the x over 2 factorial, and then some stuff squared. Really common error that I've seen. That is not it. What did we forget to do? We got to plug in. It's not f double prime of x. It's not an x here. It's a specific number a. So don't just stop after you've done your general derivatives. We got to plug in our number. So let's plug in our number here. Okay, so we're plugging in 0 because that's what we're told the value of a is. So let's give that a shot now. F of 0, f prime of 0. I realize this is kind of silly because these are all the same, but that's just because this is a really simple one. Most of the time, these will be all different numbers, and you'll actually have work to do here. F of 0 is 1, f prime of 0, 1, lots of 1s. All right, so now it's time to plug into our formula up here. So I can't have that on the screen and write it at the same time, so you guys will have to look up at that formula on your paper. So what we are saying is that e to the x is approximately equal to, okay, so the first term is just supposed to be f of a, which is f of 0, which is 1 in this case. I'm going to put the factorial on the bottom just so we see it's part of the general pattern. Which factorial is this guy? It's a 0 factorial, which a lot of folks don't like seeing a 0 in any denominator, but 0 factorial is 1, so it's okay, it's just a definition. Plus, okay, the next one is our first derivative evaluated at the point. What was the first derivative? Evaluated at 0 was 1 divided by what factorial? 1 factorial times, I'm going to write it out here, x minus what number? 0. That's the a value right there. And then I'm going to put the power up there. Just get all the patterns displayed here. Plus second derivative, what was the number? 1 factorial 2 x minus 0 squared. Okay, we'll do one more. The derivative was, thank you. The derivative was 1, the factorial is 3x minus 0 cubed plus dot dot dot. Okay, so let's clean this up so it looks a little bit nicer. Equals. The first guy is just a plain 1 plus second guy is what? Is just x. Okay. Third guy is x squared over, I'll keep the factorials from here. So x squared over 2 factorial. Next one, x cubed over 3 factorial plus dot dot dot. So far, so good. All of that agrees with what we did last class. So really the new thing for this class is that we're going to write the general term next. We're going to write an arbitrary term someplace out here in this series. So let's get another plus sign after all these dots. Typically the power that you pick is n. So let's do the nth power. So x to the n, and the factorial is n, right? Because it's just the same power as the factorial number. That's the general term. And now that we've got the general term, we can actually write in sigma notation, this thing. So let's do it here. Summation. Got our general term written, we'll just plop it right inside of this sigma, x to the n over n factorial. Yeah, let's make sure we got the right starting point. Typical choices are 0 and 1, but really could be anything. So what value of n will give you that the correct first term is 0, right? Okay, now our starting value, our ending value last class was some finite number, like 4 terms in. But today we're going forever, so let's go forever. And the thinking here is that, as we saw last time, the higher the degree, the better the polynomial approximates the starting function, right? You guys saw that graph with all the different versions, and the higher the degree, the better the approximation. So if I let this guy go forever, then instead of saying e to the x is approximately equal to this thing, I'm saying, no fooling, it's equal. Okay, and now that we've got our summation notation version of this Taylor series, we can talk about the interval of convergence. This is like one of the questions on your project. Right? The one you are currently working on looks just like this. Is here you go, 1 plus x squared over 2 factorial. And now find the interval of convergence. What test are we using? Ratio test, right? That's our standard tool for Taylor series. So let's use the ratio test. Okay, so ratio test starts with a limit. N is going to infinity. Remember, ratio test compares the next term to the current term. Which one goes on top? The n plus 1. So let's put the n plus 1 versions on top. X to the n plus 1 over n plus 1 factorial. And then it gets divided by the current one, but let's go ahead and flip and multiply. So times n factorial over x to the n. Yeah, we're missing the absolute value, and that's important. Like it's part of the ratio test, and that's the way that the x is going to be inside of an absolute value and then get trapped between two different numbers. So let's do some canceling here. Limit as n goes to infinity. Keeping the absolute value here. All right, so like I said, I'm going to hand back the take-home quiz later today. Some of us are really good at the algebra involved with canceling factorials, but some of us still need work, and we're doing very strange things, and we need to make sure we have a handle on how these things cancel. N plus 1 factorial is the bigger one compared to the n factorial. So we just think about how many extra terms will that one have. N plus 1 is the first guy, and then one less than that is just n. And then it's caught up to the guy on the top. So it's going to cancel everything except for that very first term, which is n plus 1. No factorials anymore. Okay, canceling the x's is more straightforward. You've got x to the n plus 1 on top, x to the n on the bottom. What's left? Single x where? On the top. Okay, now that's very common to just have a single x left on the top. Okay, I'll do this in 2 steps, although you might be able to just see right now what the limit is. What am I going to pull outside of the limit? Is the absolute value of x. That's why we needed to have the absolute values for that step right there. Limit n goes to infinity of 1 over n plus 1. You don't need absolute value anymore because it's all positive, but I'll keep it. What is that limit? 0. So this is absolute value of x times 0, which is always 0. This is one of our special cases. Normally you just get some number times the absolute value of x, some non-zero number times the absolute value of x. Remember the ratio test for convergence, what does that need to be? Less than 1, and 0 is always less than 1. So what does that mean about the interval of convergence? It's all real numbers, right? Because it doesn't matter what x you pick, that thing is going to be less than 1. It's 0 for every single x that you pick. So the interval of convergence is minus infinity to infinity. Easy. Normally we need to check endpoints separately. This is one of the rare cases where we don't. There aren't any. Okay. Infinity is not a number that you can plug in. X is taking on any number you want. Infinity is not a number. Okay, so that's it. Questions on that one? Okay, let's take a look at the next page. Oh, question here, Trevor. Yes. Yeah, so anything that you can do derivatives of, you can do this process. Now, the fact that the interval was all real numbers is that's not consistent. This guy approximates e to the x, and the more and more powers like this red thing written out, you will see it looking more and more like your e to the x function forever, left and right, minus infinity to infinity. But on the next page, we're going to see one where the approximation is much more constricted. It's going to look better and better, but only on a sort of small interval. Okay, Taylor series 4, f of x equals ln of 1 plus x near a equals 0. And then at the end of this, we'll actually be able to find the actual value of the alternating harmonic series. Yanni had asked a couple of classes ago, hey, do we just take it on faith that this thing is pi squared over 6 and this thing is ln of 2? And I said yes at this moment. So here's one where we actually will get our hands on why one of those magic numbers appeared. Okay, so this guy is going to be trickier because the derivatives are not nearly as nice as the e derivatives. So let's start making our list here. On the previous example, I said let's do 4 derivatives. Let's be a little bit more nebulous than that, and let's just do the derivatives one at a time until we feel like we found the pattern. That's the heart of it, is to just do enough until you find the pattern. So what number are we plugging in for x? 0, that's the value there. So this is really ln of not 0, but 1 plus 0, right? So ln of 1 is 0. Great. Okay, I don't feel like I have my hands on the pattern yet. Let's take a derivative. ln of 1 over ln of 1 plus x. 1 over 1 plus x. And then we'll plug our 0 in here. And I get 1. Do we feel like we have the pattern yet? 0 first, 1 next. Anybody ready to say 2? No? All right, let's try. Negative 2. I don't see that at all from this, but let's do some more. F double prime equals. What rule? What derivative rule? That is currently a quotient rule. Yuck. Let's do something else before we get there. This is really 1 plus x negative 1, right? I didn't have any reason to do that before, but I don't want to do the quotient rule. So there's a good reason to do that now. Now it is a chain rule based on the power rule. Okay, so derivative in that form, negative 1, 1 plus x to the negative 2, technically times the derivative of the stuff, right? And the derivative of the stuff is just 1, which makes this pretty easy. F double prime of 0. So we get negative 1 plus 0 to the negative 2. Yeah, so it's a negative 1 over 1 squared. What is that? Negative 1. Good? Okay, so any semblance of pattern finding that I was after in the beginning is just blown out of the water now. So I have no idea what's going on with these numbers, so we need more data, right? So let's do another derivative. F triple prime of x. So negative 2 comes down, makes 2. 1 plus x, negative 3, times another 1. Okay, so we plug 0 in there, we get 2, 1 plus 0 to the negative 3. 2. Right, I mean 1 plus 1 to anything is just 1. Okay. This guy? This guy? That's this power coming down and multiplying. Yeah. All right, let's do one more and we'll have more people with a pattern. Okay. So looking at these numbers, I'm still not quite sure what's going on. 1, negative 1, 2, I don't know, it could be negative 2 if it's like this repeating, I don't know. All right, let's do one more and then maybe that'll be, All right, we got a prediction on the floor, -6. Okay, so let's give this a shot. So the power comes down, -6, it's 1 plus x, so -4. Okay, so we had, again, just looking at our numbers on the right-hand side, 0, 1, -1, 2, -6. Some of us might see it here. I'm not going to write out the whole next row, but I think just getting the final number will help some other folks see what's going on here. That number comes down and makes 24, and that's going to be the answer at the end of this, yes? So 24 will be the next number. And in this class, hopefully we've seen this collection of numbers a few different times, starting to recognize it. The alternating piece you can ignore, we can deal with that separate, but just looking at the 1, 1, 2, 6, 24, we've seen those. Those are factorials, right? Those are the factorials. And do we buy that that pattern is going to continue? We wrote this guy as 6, but maybe instead of 6, we could have left it as a -3 times 2, right? That's where the 6 came from. And then the next guy coming down is going to put what in the front? It's going to put a -4 in the front. And the next one will be a -5 in the front. So yeah, I'm buying it. Those are factorials just because of the powers coming down. Okay, so let's see if we can push all this stuff into our formula. The first term is an outlier. It doesn't fit into it. Yeah. Well, no, I'm going to write it, and then I mean it's a 0, so I mean it doesn't need to fit, right? It doesn't contribute anything. I'll write it, and then we'll ignore it. Okay, so the original problem was this: ln of 1 plus x, approximately equal to. Okay, so the first term is just that first value. What was it? 0. I will divide it by the right thing just so we see all the patterns. 0 factorial, right? That's the first factorial down there. Plus. And we've got our first derivative value. What was it? It was 1. 1 factorial here. X minus what number? 0 to the first. Okay, I'll put a plus. What's the next derivative? This is the second derivative one now. It's a -1 over 2 factorial x minus 0 squared. Okay. And now we're up to the third derivative. That was a 2, 3 factorial x minus 0 cubed. Fourth derivative was what number? It was a -6. I'm going to write it in a different way. It was 3 factorial, right? The negative. Divided by 4 factorial. X minus 0 to the 4. All right, one more term here. Is it positive or negative? Right, so 4 factorial was the fifth derivative we just took. That was the 24 over, that was the fifth derivative. So that's the factorial that goes down there. And then fifth derivative corresponds to the fifth power. And when you write it, when you leave the numerators with the factorials in them, then we get another chance to practice with our canceling factorials. So let's do that. Equals. Okay, first term is just 0. I'm not going to write it. It doesn't fit the pattern, but it doesn't need to. It doesn't contribute anything. Okay, the next term is just x. Right. Is the next term positive or negative? Negative, and so it's 1/2 x to the 2. Okay, and now we're going to cancel in this next fraction. So I'm looking at a 2 on top of a 3 factorial. That's a third, right? The 2 cancels there. Okay, so then we just get plus a third x cubed. Okay, so far so good. And we've got a minus sign, so I'll put that next. 3 factorial over 4 factorial. Cancel, and what do you get? 1/4, right? Because the factorial on the bottom is just one term bigger. So that's a 1/4. X to the 4. See if you can write that last term on your own. Okay, somebody we haven't heard from yet today. What's thank you. Oops, 1/5 x to the 5th. Great. And then it goes on. We're not going to do the general term here. It's going to be the first thing you do in the activity. Okay, so we're just going to pretty much end right there. But if we plug in, for example, x equals 1, let's just see what we get. I'm just picking a number here. Plug in x equals 1. It is. So first term is 1. Next term, when you plug in x equals 1, 1/2. Next term plus a third, right? Because all these x's just become 1s, and then minus 1/4 and plus 1/5. It's the alternating harmonic, right? If you just plug in x equals 1. Now, we proved that the alternating harmonic series converged. We used the alternating series test, but we didn't know what it converged to. It's just some unknown finite number. But that thing in red is really what? Right, it's really ln. Look, it's ln of 1 plus x. That's what we've been trying to approximate. So ln of 1 plus x is this. So what is the x in our case? It's 1. So this thing, this alternating harmonic thing, must be ln of 1 plus the x, ln of 2. That's what the alternating harmonic series converged. ln of 2. All right, so before the activity, a couple of things Taylor series are useful for. The Taylor series stuff is how your calculator approximates log functions, trig functions, and exponential functions, and lots of things. Pretty much the calculator is only capable of adding, subtracting, multiplying, and dividing. That's all it can do. Anything else, it has to turn into add, subtract, multiply, or divide. And guess what? Taylor series are all add, subtract, multiply, and divide, right? Power is multiplication. And so when it comes time, like if you type in sine of some crazy number on your calculator, it is just going to say, oh, I know what the Taylor series for sine is, and I'm just going to plug into that Taylor series, whatever crazy number you put, and now all of a sudden sine becomes add, subtract, multiply, divide. They can help us calculate sums of series, so we just found that one right up there. The one that we didn't do is listed here. You can look at it later if you want. They can help us understand some new functions. Next class, we will talk about e to the I theta, and they can also help us find some derivatives and integrals that would be hard or impossible. We'll do some of that stuff next class too.
The calculator has the f on top, like function of whatever the a is. Then how does it do the sine? Because you do the derivative of sine and derivative of that.
Mm-hmm. So the calculator has pre-programmed into it. Here's the Taylor series for sine. It's one that I think was written on in the last activity. It's, yes. Yeah. So instead of sine of x, it just thinks, oh, that's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Part programmed in. Yeah, good question. No. All right, so the activity starts on the next page, but I just have 2 quick corrections to make. Can you jump to page 57? At the bottom of page 57, you see it says find the general term and the IOC. See that on the bottom of 57? So in 57, you are going to see a pattern with pluses and minuses that we don't have the ability to write down. So I'm just going to say as you write the general term, you're just going to ignore the, I'll write alternating here. It's not going to be alternating, because if it was just plain alternating, plus minus, you know how to write that. But this pattern is not that. And so when you write the general term, don't worry about the pluses and minuses. We don't have a way to write it. And then on the next page, in the answer key, this number 1 here, the IOC, it has the brackets and parentheses on the wrong things. It should be this. So -1 to 1 is correct, but swap the parentheses and the brackets. It's the middle of page 58. Everybody see that? Okay, and the last thing is I give these quizzes out. So this is really embarrassing, which is why I'll pause my recording.